Okay, hello everybody, we're starting our lecture. First lecture of the fourth week. Yep. All right. So where we finished last week, we described the microcanonical ensemble. And specifically for the microcanonical ensemble, we derive the following relation, that the entropy of the system, okay, is K Boltzmann log of omega, omega is the number of states of the system. Now, for the microcanonical ensemble, what we know is that the energy of the system is kept constant, right? It can jump from one state, or the system can jump from one state to another, but the energy is constant. We assume that the energy cannot fluctuate. And there was an additional assumption. The additional assumption was that the probability to be in any given state, okay, is exactly the same for all the different states of the system, right? So if you remember, we had this. Specifically for the energy, the average energy was a sum of all the different states of the system, is the probability to be in a given state of a system multiplied by the energy of this state. In general, we can write this relation for any observable. So the average, if we have an observable O, for example, a magnetic energy, the length of the system, or whatever, we have a specific observable. The average value of this observable is simply the sum of all possible values that this observable can have, right? So we go over all the different states of the system. We write down the values of this observable for any given state, and we multiply it by the probability, okay, to be in this specific state. Now, microcanonical ensemble, usually when we treat systems in statistical physics, we need to assume or derive the values of this energy over here, or the different values of the observable. Okay? This will depend on the model that we are using and on our observable. The value or the values of the probabilities will also depend not simply on the model, but also on the ensemble that we are using. Okay? There are some statistical properties that we impose on the system. And microcanonical ensemble is the simplest one, because here our assumption is that all the probabilities are exactly the same. Okay? So the only thing that we need to do in order to calculate the probabilities, all different probabilities, is to calculate the number of states. Okay? And 1 over this number is the probability to be in any given state. This is microcanonical ensemble, the simplest ensemble there is, right? Moreover, how to relate this to some physical observables or equations of states that we are used to deal with in thermodynamics. So for microcanonical ensemble, there is this relation, okay? The entropy is proportional, not proportional, equals exactly to K Boltzmann log of omega. Again, the only thing that we need to calculate is the number of states omega. So P, for any given state, it's simply 1 over omega. The entropy is given by this relation. Okay? Now, if we want further on to compute any equation on states, for example, we want to compute the temperature. Okay? If we want to compute the temperature of the system, the temperature is simply given. 1 over the temperature is 1 over T is ds to du, or dE, the energy of the system. Okay. So if we will obtain entropy as a function of energy, and energy can be related to the number of states that we have in our system, okay, we can perform this derivative, and then we'll have some sort of a state equation that will have a physical quantity, energy. It will have also a physical quantity, temperature. And this will be our equation of states that Now we can go backwards to all the thermodynamics that we used to solve and hate actually, and use all the methods of thermodynamics, right? Now, but in thermodynamics, we have those great general assumptions about how functions behave, if they are continuous functions or discontinuous functions. Statistical mechanics is about, okay, assumption, what are the probabilities, okay, and properties, different properties of the specific models. Okay? So we do not start with something extremely general, right? We usually say, well, we need to assume what kind of ensemble we are using. So we are using now a microcanonical ensemble. It dictates what are the different probabilities are, and then we need to treat a specific model in order to derive what are the energies of this model. What are the different observables of this model? Okay? So we are basically have to treat specific models and not something extremely general like in thermodynamics. So this is exactly what we are going to do right now. We're going to treat 3 different models for the microcanonical ensemble and see how one can calculate different observables and different quantities based on those models. So the first model is the Einstein model of solids. (1907). Okay. So what is a solid? When, at least at the time of Einstein, when people looked on it, so we know a solid is a bunch of atoms, okay, like for example in a crystal, and all those atoms approximately sitting on a lattice, right? And somehow those atoms, or the in general molecules, they're vibrating, okay? They're affecting each other, okay, and perform some sort of vibrations. Maybe not elastic vibrations, but some sort of movement that occurs due to the fact that the temperature of the solid is non-zero. So all the different molecules, all the different atoms of the system have to fluctuate a little bit, right? Now, Einstein have a very simple assumption of how to proceed from this point on. Okay? He says the following: well, if we look on all those different atoms in a system, right, their motions are highly correlated. Okay? If I will move one specific atom over here, okay, I will move it a little bit to the right, the movement of this atom will affect all the atoms in the vicinity of this atom. Okay? So the motion of this atom affects the motion of this atom, this atom, this atom, and maybe this atom, etc. Now, the moment this atom moved, it affected the motion of this atom, and then this guy will affect other neighbors, right? It will affect all the other neighbors in its vicinity, and maybe at some point also affect backwards, right? So they are cooperating in a very intricate fashion, and it's actually really complicated to calculate how exactly all those atoms moves. Moreover, it's already 1907, so people started those Planck experiments. There is some sort of a notion about that it's not a simple classical mechanical description. There is something new going around over there. Okay, so, and already today we know that we need to use quantum mechanics in order to describe the motions and the behavior on atomic scale. So all of this is very, very complicated. Okay, how are we going to actually solve it? So here is the regular approach of physics spurs out. Okay, what is the really, really, really beautiful approach of physics? Let's neglect almost everything and keep only the essential stuff. So what is the simplest problem that a physicist can solve? And it's almost the only problem that a physicist can solve. It's a problem of harmonic oscillator. Okay, so let's assume, okay, this is what Einstein told us. Let's assume that all of this, okay, we have n atoms inside our solid. let's assume that all of those atoms are simply harmonic oscillators and they do not affect each other. Right? So it's basically, we have 3n degrees of freedom because each oscillator can oscillate in the x direction, in the y direction, and in the z direction. Okay? So we have 3n degrees of freedom, and the most naive assumption is, let's assume that all of those degrees of freedom are basically independent of each other. Okay? So this is the naive assumption of Einstein for the model of solids. All right. How we proceed? So what else is known in 1907? So we know, well, they already start to understand that the system can absorb quantas of energy. Okay? This is the Planck's experiments and explanations of Einstein for the photoelectric experiment. Okay? So the assumption of Einstein is that each energy, there are quantas of energy, let's call it En, equals to h bar omega multiplied by n. So each harmonic oscillator over here, okay, this can have n quantas or n parts of h bar omega. Right? So where this comes from? Well, this actually occurs from the solution of a harmonic oscillator, the regular harmonic oscillator. Okay? If we will write this down in a quantum mechanical way, we will take an oscillator, we write an Hamiltonian. So the Hamiltonian of any regular oscillator is operator p squared divided by 2m plus 1m omega 0 further x squared. Right? We can solve it. We'll obtain eigenfunctions of the form. It's a long form. I never remember it. So it's 1 over square root of 2n n factorial m w0 by h bar 1 over 4th e to the minus m omega 0 x squared divided by 2 h bar. And here we have the Hermite polynomials, square root of m omega 0 h bar x. It's a really, really, really lengthy form, but the only thing that matters, okay, when we solve all of this, okay, we'll probably solve it in the class on quantum mechanics, you obtain that and the energies of a harmonic oscillator are always of the form of n h bar omega 0 plus 1/2 h bar omega 0. Okay? So omega 0 is the frequency, and all the different energies we can also put at En over here. All the eigen energies are simply n multiplied by h bar omega, okay, and shifted by 1/2 h bar omega 0. So the assumption of Einstein was, well, let's forget about this 1/2 h bar omega 0. Why? Because it's only shift. Okay? We don't really care from what energy we are starting. So there is a zero energy. The zero energy is 1/2 h bar omega 0. All the other energies of the system is basically an integer number, n, and can be 0, 1, 2, 3. Okay? An integer, positive integer number that provides us with the total energy of each harmonic oscillator. Okay, so if the system, so if we take this description and assumption of Einstein and we say each harmonic oscillator, the energy is simply h bar omega multiplied by n, and the total number, okay, the total energy of the system is U, total energy of the system, then U divided by h bar omega what is U divided by h bar omega, is the total number of quantas of energy that must be spread between 3n degrees of freedom. Okay? So let's assume that we have only 2 oscillators, right? Or 2 degrees of freedom. And I'm saying to you that the total energy is 4 h bar omega 0. Right? So if we have 2 oscillators, 2 degrees of freedom, the total energy is U equals 4 h bar omega, okay? N equals, or 3n equals 3. So we have only one oscillator, but it has 3 degrees of freedom in x, in y, and in z. So we know that U divided by h bar omega equals 4. Okay? So what we know that we somehow need to push this 4 h bar omega 0 into 3 different degrees of freedom. We can say, well, you can have an energy in the oscillations in the x direction, 4 h bar omega, and you will have 0 h bar omega at the y and the z direction. Or you can say, no, we can say that we have 2 h bar omegas in the x direction, 1 h bar omega in the y direction, and 1 h bar omega in the z direction. Okay? The total number of states of the system, okay, is the total number of ways that we can basically change the types of, or how we can assemble those quantas of energy into 3n degrees of freedom. In this case, okay, is how 4 basically can be divided into 3 different groups. Okay? So in total, we have U divided by h bar omega 0. We have 3n degrees of freedom. Somehow we need to compute, in order to compute what are the different number of states in the system. The different number of states in the system is the number of ways such that U divided by h bar omega 0 can fill out this 3n different degrees of freedom. This is a combinatorial problem now, right? So what we actually doing? Let's assume that we have U divided by h bar omega 0 balls. And we need to put them into 3n different boxes. The different number of ways that we can put all those balls in all of these different boxes is the number of states of the system. Okay? The same as what I was trying to describe to you here. One state, for example, is all these 4 h bar omegas are in the x direction. Another states, 2 in the x, 1 in the y, 1 in the z. Another situation, 3 in the x, 1 in the z, 0 in the y. Okay? I need to count all of them. Now, how one solves this problem over here? So let's assume we have balls, and instead of boxes, I'm trying to say, so we have, those are our boxes. Let's forget about that the boxes, if we have, the boxes are kind of sticks that we put between the balls. So we can basically have all those balls, right? And somehow we need to put different number of separating walls between the different balls in the system. So we need to count the number of ways such that we can interchange this separators and the different balls, okay? And each specific feature is one way or one state of the system, and we need to count all of them. Now, how many separators I have? So balls I have U divided by h bar omega 0. Those are the quantas of the energies. I have 3n boxes. So instead of, say, using boxes, I will use 3n minus 1 separators. Okay? So if, for example, if I need to use 3 boxes, Okay? If I need to use 3 boxes, those are my 3 boxes. Box number 1, box number 2, and box number 3. So instead of speaking in terms of boxes, I'm speaking in terms of separators. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 balls and 2 separators. And I need to interchange all of them, okay, in order to get a count of all the different states. So the number of states, let's call it omega, okay, is 3n minus 1 plus u divided by h bar omega 0 factorial. Okay? So this is the total number of all the different interchanges of the separators on the balls. Now I need to divide them because I don't care if I have separator here and separator here and then I interchange their position. It's still the same state, right? So I need to divide everything by 3n minus 1 factorial. And I also don't care if I will take those 2 balls and I will interchange them position as well. Okay? It's still the same state. I have still 2 quantas of energy in a box over here. I don't care, so I need to divide everything also by u divided by h bar omega factorial. So this is our equation for the total number of states in this system over here. Okay? We only need to count. This is always the situation with microcanonical ensemble. All the different states are equally probable. The only way to somehow solve anything or obtain an equation is to count all the possible states. You will always get some cumbersome formula which is related to divisions of different factorials because you will count states in the microcanonical ensemble. Okay? This is the easiest ensemble, but mathematically the most cumbersome. All right. So what do we need to do? We want to calculate eventually, right? What do we want to calculate? We want to calculate the entropy, which is K Boltzmann log of omega. Okay? Omega is this guy. Now factorial is a nasty function. I don't want to use factorial. Let's assume that the number of atoms in our solid is pretty big. Okay? So we're talking about a macroscopical system, and the n is large. When n is large, okay, I can make some sort of approximations. I'm looking on this guy, I'm saying, well, log of 3n minus 1 plus u divided by h bar omega factorial divided by 3n minus 1 factorial and u divided by h bar omega factorial, okay, it equals to log of 3n minus 1 plus u divided by h bar omega factorial plus log of whatever is left here. So it's 3n minus 1 factorial u divided by h bar omega factorial. So I need to compute the logarithms of different factorials that I have over here. Minus, thank you, sure. Yep. Yes?
And how does it make sense to assume that n is large when you're using a microcanonical ensemble? Doesn't microcanonical imply a small amount?
No. Microcanonical ensemble imply that the energy is constant. I don't care what the size of the system is. Micro is not about the small size of the system. Okay? Because there is canonical and microcanonical. Microcanonical, the only thing that it implies, okay, that the energy of the system is constant. That's it. Now physically, any physical system, you can ask the following question: is microcanonical ensemble real? Okay? This is a different question. Okay? But it's a sort of approximation to all the different ensembles and representations of systems that there can be. Okay? This is a model for a system. It's not really useful, as we will see, but it teaches something about how specific calculations are performed. Okay, so what can we do with the logarithm of a factorial? What can we use? Stirling, right. So there is a guy named Stirling, and he thought about an approximation for the logarithms of factorials. Basically, n minus n plus 1 factorial. It is a gamma function of n, right? And it equals to an integral from 0 to infinity x e n minus 1 e minus x dx. Right? Now, have you learned about stationary phase approximations, Laplace integrals, and stuff like that? No. Never mind. But basically, you can take your, maybe someday we'll learn a method about how to approximately calculate different integrals of such form. Okay? So you can expand this integral and compute an approximation. And eventually what Stirling approximation means is that log of n factorial, when you use an approximation to this integral, equals to n log n log n minus n. Okay, there are some additional terms that we don't really care about, some pi's and pi's multiplied by n and log of n and etc. 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 So this is the Stirling approximation. Stirling approximation. All right, so the moment we have Stirling approximation, we can start and calculate all those nasty terms that we have inside here. Okay, so let's start and do it. So we have a log of 3n minus 1 plus u divided by h bar omega multiplied by, it's nasty, multiplied by 3n minus 1 plus u divided by h bar omega. So this is n log n minus n, so minus 3n minus 1 plus u divided by h bar omega 0. Okay. Now let's look on this term. So here we have minus 3n minus 1 log 3n minus 1, okay, plus 3n minus 1. Okay, and the last term is the logarithm of u divided by h bar omega factorial. So here we have minus u divided by h bar omega multiplied by log of u divided by h bar omega plus u divided by h bar omega. All of this, okay, is what? Is S divided by K Boltzmann. So all of this equals to S divided by K Boltzmann. Now, this is already something that we can work with. So here all the physics stops and we need to perform those mathematical calculations. So what exactly I am trying to find? I want to get rid of some of the terms over here. Okay? And the way to perform it is actually to expand all the different logarithms. Okay? To try and expand all the different logarithms. So let's look on this logarithm over here. So we have a log of 3n minus 1 plus u divided by h bar omega. It equals to a log of 3n minus 1 multiplied by 1 plus u divided by h bar omega. Divided, I'm sorry, let's write it down. 1 over 3n minus 1 u divided by h bar omega. Okay. And this guy, it's simply a log of 3n minus 1, okay, plus a log of 1 plus 1 divided by 3n minus 1 u divided by h bar omega. Okay. Now look, so we have this expansion. Okay, we have this expansion over here. We can look on this guy and say, well, instead of having 3n minus 1 plus h bar omega multiplied by this log over here, okay, what we are doing is we are taking this log, and instead of this log, we are using those two functions over here. Okay, and then we're performing a multiplication. So we have 3n minus 1 plus u divided by h bar omega multiplied by 3n minus 1. Here we have minus 3n minus 1 plus log of 3n minus 1 multiplied by log 3n minus 1. So this guy and this guy, okay, they cancel each other. Okay, the same goes for 3n minus 1 over here, minus 3n minus 1, and plus 3n minus 1 over there. Okay, this we already can see over here. So 3n minus 1 minus 3n minus 1 plus uh bar omega minus uh bar omega. Okay, all of those guys disappear. On the other hand, okay, so we killed also this guy and this guy that was multiplied by 3n minus 1 and log 3n minus 1. Okay. On the other hand, okay, this expansion can be done in the following fashion. So here we have uh bar multiplied by log of 3n minus 1 plus u divided by h bar omega. Okay. We can work it out the other way around, and we can say, well, this is uh bar u divided by h bar omega multiplied by log of u divided by h bar omega, okay, plus log of 1 plus 3n minus 1 divided by uh bar omega. Let's write it down. Let's write it down over here. So what I'm trying to say is as follows. I'm taking this form and I'm substituting it over here. Later on, I'm taking another form and I'm also substituting it inside this guy. Okay. I think I have to write it down. So let's see. So we have 3n minus 1 multiplied by log of, instead of this guy over here, I'm using those two functions, log of 3n minus 1 plus log of 1 plus 3n minus 1 u divided by h bar omega. Okay. I close my parenthesis. We have u divided by h bar omega multiplied by log of, let's keep it still, 3n minus 1 plus u divided by h bar omega. Okay. All of those guys, this and this and this and this, I don't care about them anymore. Okay. So we have an additional term here, minus 3n minus 1 multiplied by log of 3n minus 1. Okay, and we also have minus u divided by h bar omega log of u divided by h bar omega. now you see what else we have. So here we have this term 3n minus 1 multiplied by log of 3n minus 1. Here we have minus 3n minus 1 log of 3n minus 1. Those terms disappear. Okay? We're doing this slowly. So I'm left with 3. I'm left with 3n minus 1 multiplied by log of 1 plus 1 3n minus 1 u divided by h bar omega. Okay, this term over here. I will expand this guy as plus u divided by h bar omega of log of u divided by h bar omega, okay, plus log of 1 plus 3n minus 1 divided by u h bar omega. Okay, so I have taken this guy and I've separated it into two logarithms, and I have a minus of u divided by h bar omega of a log of u divided by h bar omega. Okay, so now I can also kill those terms over here. Okay, so what we are left with? It's a very simple and straightforward algebra. It's just long, and it's even going to be longer. All right, so we are left with S divided by K Boltzmann equals to, we have this term over here, 3n minus 1 multiplied by log of 1 plus 1 over 3n minus 1 u divided by h bar omega plus u divided by h bar omega multiplied by log of 1 plus 3n minus 1 divided by u divided by h bar omega. Okay? So this is our entropy. Okay? Now entropy here depends on the number of atoms, okay? Omega, so the self-oscillation of the harmonic oscillator, and also U. What is U? U is the total energy of the system. Okay? Now we can say, wait a minute, I know something. I know that 1 over T is ds to du. I have S, which depends on U. We can sign it over here. Now I can only to take the derivative with U, with respect to U, of this guy, and I will get something that's relating a function, okay, and temperature. And this will be our state function. Okay, so let's do it. So the derivative of S with respect to U is, so what we have over here, we have 3n minus 1 multiplied by 1 over 1 plus 1 over 3n minus 1 U divided by h bar omega multiplied by 1 over 3n minus 1 multiplied by h bar omega. Okay. So this is the derivative of this term over here. Additional derivative that we have, this equals 1 over t. Additional derivative that we have plus we take the derivative of this guy over here, which is 1 over h bar omega, multiplied by a log of 1 plus 3n minus 1 divided by h bar u divided by h bar omega, okay, plus u divided by h bar omega multiplied by 1 over 1 plus 3n minus 1 h bar omega divided by u, and the inner derivative of 1 plus 3n minus 1 divided by h bar omega is minus, right, we have minus 3n minus 1 h bar omega divided by u to the second power. And this is a really nasty form. Times k, you are right. Where should I put k? Where should I put k? So can I put over here? It will be fine, right? So s divided by kb, okay? This is the form that I took derivative of. So 1 over t is ds dkb. I multiplied by kb two sides of the equation. So kb divided by t is whatever is written on the right hand side of this equation. Can we do something nicer with this thing? What do you think? Yes, no, yes, no. Okay, let's look on this ugly stuff. So it's actually not so ugly. It's actually nice. Yep. So look on this. So here we have 1, 3n minus 1 u. Okay. Here we have u h bar w, 1 plus 3n minus 1 h bar w u. Okay. Here u squared. Let's forget about this term for a second and only look on those two terms over here. So in the first term, this guy and this guy, they disappear, okay? And in this term, we can kill u, and we can kill u squared, all right? What else? We do have h bar omega, and we do have h bar omega over here, right? So let's write it down. I can kill the u as well. What u?
You multiply the 1 by u.
This?
No.
This?
No, down below.
This?
No, no, the one to the right.
This?
Yeah, down below. You see, you can take it to the top, multiply the 1 by
Yeah. I'm going there. I'm going there. Yeah, I'm going there. So we have 1 over 1 plus 1 divided by 3n minus 1 h bar omega, and we have u over here, right? And we have, what we have else? We have 1 over h bar omega, 1 over h bar omega, okay? This is from this term, whatever is left. From this term, we have minus, okay, minus, and we have 3n minus 1, okay, we have 3n minus 1 divided by u plus 3n minus 1 h bar omega, okay, plus 1 over h bar omega log of 1 plus 3n minus 1 divided by u divided by h bar omega. Okay, and this actually becomes quite nice. Why it becomes quite nice? Because look at this term over here. Okay, what this term equals, all of this term. Okay, it actually equals to 3n minus 1 divided by u plus 3n minus 1 h bar omega. All of this guy, exactly this. and it is minus 3n minus 1 u divided by plus 3n minus 1 h bar omega. Okay, so I can get rid of those two terms as well. And luckily for us, we're left with quite a nice expression. What does this expression look like? So we have K Boltzmann T on the left hand side, and on the right hand side we are left with this guy over here, which is 1 over h bar omega O. Okay, so there's a problem. We'll solve it in a second. Log of 1 plus 3n minus 1 h bar omega divided by u. Okay, what is the problem? The problem is that the KB is in the wrong place. Okay? Why it's in the wrong place? Because I put it in the wrong place over there. Where should it be? Lemata, okay? On the downside. Thank you for telling me this. It's 1T K Boltzmann or K Boltzmann T. How I've seen it, units. K Boltzmann T need to be of units of what? Of energy. Okay? S is unitless in some sense. Alright? And it's divided, so ds du should give me 1 over energy. So I should have 1 over K Boltzmann T on the left hand side in order to get the units right. Okay, so I have 1 over K Boltzmann T h bar omega log of this guy. So I have e to the power of h bar omega divided by K Boltzmann T, energy divided by energy, so it's unitless, this is great, equals to 1 plus 3n minus 1 h bar omega divided by u. Okay, so from this guy, what I obtain is that u divided by h bar omega, okay, equals to, what it equals to? 1 over 1 e to the power h bar omega divided by K Boltzmann T minus 1, okay, minus 1 divided by 1 over 3n minus 1. No? Right? Multiplied. You're right. 3n minus 1. So u divided by 3n minus 1, or I can write it down a little bit differently, but exactly the same. We have u divided by 3n minus 1, okay, equals to h bar omega divided by e to the power of h bar omega K Boltzmann T minus 1. What is u divided by 3n minus 1? U is the total energy. 3n minus 1 is approximately 3n, okay? So it's the total number of degrees of freedom in our system. So u divided by 3n minus 1 is the energy per degree of freedom of our system. And we see that it equals to this form h bar omega divided by e to the power h bar omega K Boltzmann T minus 1. We will see very frequently during this class expressions like e to the power something, which is energy, h bar omega in our case, divided by K Boltzmann T minus 1 plus 1, etc., etc. We will see expressions like this very, very frequently. So according to Einstein, okay, there is an average energy per degree of freedom, and it is of this form. Okay. Was this a success of Einstein or not? We will later on, we will see, so it's actually not such a useful model, and the only limit where it works is only the limit when the temperature is very, very high. In the limit of high temperature, this model gives pretty nice results. But when the temperature becomes smaller and smaller and closer to zero, okay, the prediction of this model is absolutely wrong. Why it's so? Well, you can think about it yourself. When the temperature is very, very high, all the different atoms will start to vibrate very harshly. They won't care about each other at all, right? And then we can indeed assume that the system is composed of all three different harmonic oscillators. Okay, so this is right for the t goes to infinity limit. The problem that when we're going to the small temperatures, this assumption of Einstein that this atom won't care about its neighbors, and those neighbors won't care about the atom and the other neighbors, it falls down. How one can see it, one can, or how they discovered 100 years ago, they computed something that is measurable in experiment. Okay? For example, the heat capacity. Heat capacity is du to dt. Okay? You have now an expression, a prediction from your theory of how the heat capacity should behave with the temperature. You can compute it, and then you can go to experiment and measure the heat capacity in experiment, and you will see that they will give very different answers. For the Einstein model, you can do it yourself. This heat capacity will behave exponentially. It will grow exponentially. For the measured heat capacity, it grows as a polynomial of the temperature. Okay? So there is a big difference. You can say, well, polynomial, exponential, but there is a huge difference in behavior. Okay? Where it comes from? It comes from the fact that we neglected all the cooperative motion that can happen in a solid. Motion of atoms are not like this. They are extremely cooperated when they are in a very low temperature limit. And when you neglect it, something awful happens. You can do it for high temperatures, but you can basically throw it away, but you cannot throw it away for the low temperatures. And this is what happened in Einstein model. This is not so useful model. It's conceptually interesting that you can basically forget about almost everything for a solid in order to describe its statistical behavior, and you can say, well, I have a bunch of independent particles, independent oscillators, and it works. It won't work for low temperatures, but for high temperatures, all of this works. Okay? You can use this description equation of state, and it still works. Although you used microcanonical ensemble, we will see later how to improve this assumption. All right. So we've seen the Einstein model. Let's solve another model. Still have some time. Any questions so far?
Yes.
Yep.
Isn't it supposed to be e to the power of h bar omega plus 1, not minus 1? Because if t is going to...
This guy. Okay, so this guy was 1. I moved it to this part and then inverted. You're saying that there is something wrong with the formula eventually?
No, I'm just asking because you said if we take high temperatures, t goes to infinity.
Then you will have to expand it. You will expand it and you will see it actually behaves nicely. Don't worry, we will calculate specifically the specific heat for a canonical ensemble, and you will see how this works. Right? The microcanonical ensemble is not really interesting. It's just a way of how you think about problems. The other model, yep. האנרגיה לחלקיק. Okay, so the question is, if my temperature is going down, the energy, or is going up, okay, the energy per particle is going up.
Down.
Why? Its T goes to up, all of this goes to 0, and U divided by 3n explodes, right? And this is actually makes sense. You increase your temperature, so every oscillator have much more energy there, okay? It's the denominator. No, I don't remember what's nominator, what's no denominator. Machane. Okay, any other questions? You will see during this class that why this is actually important. The importance here is that physical systems are extremely complex. Extremely complex. I don't know how to solve whatever is happening in this pencil. I don't know. The only thing that I can actually solve as a physicist, and we started with this in our first lecture, is a particle, okay, or two-body problems. Whenever I have three-body problems, okay, I'm starting to fail. I don't know what to do. What Einstein did over here said, well, it's very complex, and the only thing that I can solve is one particle, one-body problem. Even if I'm talking about general relativity, etc., 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 it's all about one-body problem, right? So let's assume they are all independent. We will see that this idea, it's extremely important because whatever we are going to do, and whatever is done in physics, or in different other aspects of science, is always to represent complex problems as a bunch of a huge number of very simple problems. Okay? This is how computer works. For example, right? Instead, we have a very difficult task, and we simplify it by doing a lot of very simple tasks. Exactly this is what's going on in statistical physics. Okay? We will have a very complex situation, and we will try to present this, okay, as a sum, maybe, or an ensemble of different very simple systems. Those systems can be maybe not very intuitive, right? But we will see that this is the only approach that works. Because the moment we will start to assume, well, we have three-body interactions, four-body interactions, we are doomed. We cannot advance. We can maybe push everything inside a computer program and run a simulation. If we want to gain an understanding, we will always try this approach of representing everything as systems that do not interact. Einstein was wrong. Why? Because he assumed it from the start. Okay? The actually nice way to do it is to start from a complex system and try to represent it, find a representation of the system as a bunch of non-interacting particles or non-interacting systems. This is what we will do for the end of this class. We will take a complex system and we will try to represent it as a non-interacting system. It might be not those atoms, it might be, you know, some complex variables that depend on the positions of these atoms, but this is our approach is going to be. The other system, it's still very, the other model, it's called a two-state model. So what is a two-state model? So we have n particles, and each particle can have only two energies. It's even simpler than the Einstein model. For each particle, there is 0 energy and epsilon energy. Okay? That's it. So the particle can occupy either a state with 0 energy, or it can occupy a state with epsilon energy. And we have n particles. Okay? Simpler than the Einstein model. So we want to derive some sort of equation like this, okay, that relates the energy to the temperature, so we can compute something like the specific heat, something that we can go and measure in a lab and in experiments, make predictions, understand a little bit about what's going on in the system. So our first goal is to write the equation of state for the system. Very simple system. And the only thing that we can do right now, we're going to assume, well, we will use the microcanonical ensemble, okay? And we will use the expression for the entropy in the microcanonical ensemble. So it's simply K Boltzmann log of omega omega is the number of states of the system, while we're assuming that the energy is constant. Okay? This is the assumption of microcanonical ensemble. Constant energy, let's find the number of states. The probability for each state is 1 over omega. We can calculate everything. Okay? So we are assuming U is the energy of the system. There are n particles. What is the different number of states inside this system? So I already told you that the way stuff works in microcanonical ensemble, we always count something. Okay? Now each particle can have either 0 energy or epsilon energy. Okay? So if our total energy is U, the number of sites that have epsilon energy is what? U is the total energy. Each particle can have either 0 or epsilon. Okay? I'm asking if I have energy of U, how many particles are occupying energy epsilon? U divided by epsilon, right? That's it. So U divided by epsilon. So the number of different states in this system, okay, what is the number of different states in the system, is the total number of the particles that I can have divided by the total number of particles that are occupying energy epsilon, and divided by the total number of particles that are occupying energy 0. This is omega. Because I don't care about all the different permutations, right? The total number of particles I have is n. I can permute all of them, okay? But the only thing that it's important, okay, that I will have U divided by epsilon particles that are red, and I will have n minus U divided by epsilon particles that are blue. That's it. So how many different ways there are if I have n particles and U of them are red and n minus U of them are blue. Okay? This is the different number of permutations. So the next step is to compute this ugly form over here using the Stirling approximation. So my clock is dead. You will have to tell me when it's 5:30. Okay? I don't know what time it is, so if you don't want me to continue till 8 o'clock, you will have to stop me.
How will you know it's 8?
Sorry?
How will you know it's 8?
Don't worry, I will know. I'm sure you will tell me. Yeah, sure. Okay. Entropy is K Boltzmann log n factorial divided by U epsilon factorial n minus U divided by epsilon factorial. Okay. And this TB's task is K Boltzmann, or let's write it S divided by K Boltzmann equals to log of n factorial minus log of U divided by epsilon factorial minus log of n minus U divided by epsilon factorial. And now we are going to use Stirling approximation. So basically log of n factorial equals to n log n minus n. And we are going to perform this tedious task of computing different logarithms of different functions again. All right, so what we have over here, that S divided by K Boltzmann equals to n log of n minus n minus u divided by epsilon log of u divided by epsilon plus u divided by epsilon. Okay, what else we have over here? Minus n minus u divided by epsilon multiplied by log of n minus u divided by epsilon plus n minus u divided by epsilon. All right? Now we do the same trick as we've done before. We expand this guy. Okay? We expand it. It's not even an expansion, right? We're just using some multiplications of logarithm of n minus u divided by epsilon. That's it. So,
question?
Yep.
I'm not sure if the u over epsilon and the n minus u over epsilon, all of these are large, because if the temperature is very high, then over epsilon must be a large number, and n minus u over epsilon must be a small number.
So the solution is everything is large enough so that the Stirling approximation works. Okay, but it's actually, it doesn't have to be so. Okay, so the Stirling approximation, it's quite interesting. Okay, so when you develop it, okay, you're assuming. The question is, I will translate the question or explain the question. The question is, you have to assume for the Stirling approximation that you have a large parameter. Okay, so log of n factorial equals to n log n minus n. So n must be large. Here I have n, which must be large. U divided by epsilon is also have to be large because I've expanded it in a factorial. And also n minus u divided by epsilon also have to be large, right? So what is larger? Maybe this is a small number. Who knows, right? And the answer is, well, I assume that everything is large, but I don't have to do this. Okay, why is so? Because, well, when I'm writing down this equation, I'm saying this works for when n is large enough, or Stirling have developed this approximation with n when n is large enough. But when you go and you try to plot, okay, you try to plot this approximation. So you plot log of n factorial, and you plot n log n, okay, and you ask yourself when it works for what n, and the answer is for n equals 3 or 4, it works excellent. The precision is excellent. Okay, so n doesn't have to be large. n4 is not a large number, and the Stirling approximation already works wonderfully. Especially if you add here this additional numbers, it's just perfect from n equals 1.7, right? So this approximation is extremely good even when n is not so big. Okay, so this is why I don't really even have to assume that everything is big. Okay, 4 is not a big number. Okay, so here I expand everything. You see those 3 dots? That means a lot. And eventually we are getting to what? So we're getting to the final equation that is important, that it's u divided by epsilon minus n multiplied by log of 1 minus u divided by n epsilon minus u divided by epsilon log of u divided by n epsilon. Okay? I simply expanded there the different logarithms. Okay? The moment I have done this, I can write down what is 1 over t. Okay? Or more specifically 1 over k Boltzmann t equals d to du of all of the stuff that I have over here, of u divided by epsilon minus n of a logarithm of 1 minus u n epsilon minus u divided by epsilon logarithm of u divided by n epsilon. Okay? And when I do this, what I obtain is that 1 over k Boltzmann t equals to 1 over epsilon, a logarithm of n epsilon divided by u minus 1. So what's the solution of this guy? The solution of this guy is that e to the power of epsilon divided by k Boltzmann t equals to n epsilon divided by u minus 1. All right, so this means that n epsilon divided by 1 plus e epsilon k Boltzmann t, okay, equals to u. This is the equation for the energy of a two-state model. Right? We have this state equation of state. What's important, or actually important, about this model, that it has a very specific behavior for the specific heat. So the specific heat, CV, it's du to dt. So we take a derivative of this guy over here, and we obtain n epsilon squared divided by k Boltzmann t. And inside of this guy, we will have e to the power epsilon divided by 2k Boltzmann t plus e to the minus epsilon divided by k Boltzmann t. There is no 2 over here. To the power of minus 2. Okay. So this is the CV. And what's important about this guy, okay, then when we plot this, and this is something that we can go and measure experimentally, what we will see that the specific heat of the system will start to rise. It will rise up to a specific point. Okay. It will have a maxima, and then it will go down. Okay? This maxima has a specific name. It's named the Schottky hump. Okay? And when in an experiment you see something like this, well, you start to understand that you have a two-state, or you approximately can describe your system as a two-state system with two definite energies. Why is that? Okay, so at the beginning your specific heat is going up. Why it's going up? Well, you have two energies, right? Very, very low temperature. All the particles prefer to sit, always prefer to sit at their possible energy there is. So everything is at zero energy, right? You add temperature to the system, you heat it up a little bit. When you heat it up, there are fluctuations. So all the different particles, or some of them, from time to time will jump from the zero state to the epsilon state, okay? And as you heat the system more and more, you increase the temperature, more particles are jumping to the excited state with energy epsilon, right? So your specific heat is going up. The more temperature you add, the more occupied excited states you're getting. Okay? Your specific heat is going up. The derivative of the energy with respect to your temperature is going up. You add temperature, you add heat to the system fluctuates more excited states are occupied. So you reach some point when there is a maximum. Why there is a maximum? Because when the temperature is high enough, and you only have n number of particles, you hit the system a little bit more, all the excited states are already occupied. There are no other additional excited states. You hit the system a little bit more, there are almost no particles at the zero energy. They are all occupied, or they're all excited, right? So you increase the energy, and your system, your temperature, basically is not growing. Nothing really happens. Okay? So this is where you will have a decrease of your energy, or du to dt will go to, it will go towards zero, right? Because U is saturating. You're going to a very constant U. The maximum energy that you can have for a system, okay, is the number of your particle n multiplied by epsilon. That's it. Okay, so you cannot get an ever increasing specific heat. It has to go down because the derivative of U with respect to T has to go to zero. So when you see, or at least 100 years ago, 50 years ago, when people measure a specific heat of the system and they see a hump like this, well, they can understand our system is approximately a two-state system. It might be a very, very complex system, but I can describe it by using only two sets of energy. Now, sometimes something even more interesting happens. Okay? Let's think that our temperature can be increased even further on. Right? So it will continue this line. It will go towards zero. And then suddenly a second hump will appear. Okay? And you will continue on and on and on. And a third hump will appear. What this means, what the second hump means. Another level, exactly. Okay? So let's assume that this is the energy of each particle. We have 0 and we have epsilon. Because they are separated, there is a specific gap between 0 and epsilon, we are having this hump, the first hump over here. Afterwards, because there is nothing above epsilon, okay, you increase the temperature, the particles try to get up, it has nowhere to go, okay, so it's basically staying at the excited state. The specific heat goes down. But suddenly, you have additional maxima. What it means when your temperature becomes very, very high, or at least much higher than this temperature over here. This means that there's somewhere over here additional energy that you have found. So you pushed your system, all of your system, to explore an additional excited state. Okay? So this is appearance of additional hump. Third hump, somewhere over here you have E2, and etc., etc., etc. So for simple systems, okay, that have gaps between energies that are large enough, you will start to see maxima in the specific heats that correspond to those gaps. Okay? So this is how you can penetrate inside your system. Instead of using a microscope, you can simply heat up the system. Okay? You heat it up and you explore the different energies of the system or the different structure of the system by simply heating the system. That's it. Okay? So instead of looking inside and saying, well, I have an atom over here and those atoms cooperating somehow with different atoms and there are spectral gaps in the energies, okay? Instead of using optics, you can heat the system and use temperature and obtain those different maxima that will correspond to different energies of your system. I think it's time. What time is it right now? Okay, so we have another model to solve, but it's a very long model, so we'll leave it for tomorrow. And that's it for today. Thanks.